Hello everyone, welcome back to Mindmatrix YouTube channel. I'm Sachin. So today we will be continuing with our machine learning lectures. Okay. Today we'll be talking about yet another important topic. So in the last session we have already seen the basics. Okay, what exactly is machine learning all about? We have seen all that and we have understood the simple jargons. So in this lecture we'll be talking about cross validation, which is one of the most important topic from the gate exam, and I know like it is important. So there is a high probability you'll be getting question from this. Okay, high probability. So I'll be trying to explain it in a way so that you understand it. Okay, and not just understand it, you'll be able to assimilate it, and I will be explaining in as simple as possible language. Okay, so I'll be discussing cross validation in detail, and we'll be talking about disadvantages, or what exactly if I talk about the types of cross validation, so within that the disadvantages of each, and then why do we have cross validation and all that. So I'll be talking about all that stuff. Okay, so before proceeding further, I would like to make a request. So guys, like, I can see the analytics that many of you are watching these lecture series, and like, you are enjoying, you are coming back to back to watch out the series, but you're not subscribing, you're not liking the sessions. Kindly do that. That motivates us to bring more content, quality content for you guys. Okay, so it's a humble request, just do that. So okay, so let's just proceed further. So there is a brief intro about myself. If you're following, then you know. If you don't, then this is like, you can just go through that. I won't be wasting time on this. So let's proceed further. So today's agenda is all about cross validation. So I'll be talking about what exactly is a cross validation and why do we need it, and then further what are the different types of cross validation. And okay, you have done cross validation. What after that? What exactly you have got? What is the outcome from cross validation? What you have got? Okay, so I'll be talking about all that in detail. So let's start with what first of all. So let me just take some examples to explain why do we need cross validation. Okay, let me just start with that. So let's suppose, just assume, okay, there is a small child. Okay, there is a small child. Okay, and then there are few pictures. Okay, there are few pictures. Let's suppose, let me just show you. Just give you an example. So let's suppose there are overall 5 pictures. One having dog, then another having cat, maybe lion, horse, and let's suppose a duck. Okay, let's suppose there are these five uh, 5 pictures you're having, and this is a child. Okay, which is in like 2 to 4 years of age. 2 to 4 years of age. Okay, I guess they can identify pictures in that age. So what do you do is you want to kind of see that how does your child learn. What am I saying? That you want to see that how does your child learn. Okay, so you are repetitively just showing these 2 pictures, or you're just showing these 2 pictures. Let's not talk about repetitively. You just shown these 2 pictures, and let's say you have shown this 2 3 times. Okay, so maybe the next time you'll ask from this, he may not be able to identify, but yeah, if you just increase it a few more times, the child will be able to recognize, okay, it's a dog and it's a cat. He will be able to recognize, or she will be able to recognize, that it's a dog or a cat. But what about if you show them the new pictures of lion, horse, duck? Will it be able to identify that? The answer is no. So just tell me, will you be able to tell that, okay, my child has a good learning power, or he learns better, or should I say that, okay, like, he can identify things very easily? Would you be able to see that? The answer is simply no. If you are judging on the basis of a small set of pictures only, if you are judging on the basis of small set of pictures, if you are again showing a kind of dog or cat, then it is possible, okay, that he will be able to identify. I'm not saying that, okay, the same picture is being shown. Maybe another dog picture is shown. Maybe another dog picture is being shown. So this kid would be able to identify with a good probability that it's a dog. Okay, some different picture of dog, because you have shown this type of picture a lot many times. but he will not be able to identify lion, horse, or a duck. Yes, because he hasn't seen it. Okay, but what if I say that you are showing all these pictures? Okay, you are showing all these pictures. In that case, what will be happening? In that case, what will be happening? You are showing all of these pictures. Basically, dog, cat, lion, horse, or duck. So in that case, it's like quite easy stuff. Okay, that you will be able to say that okay, now lion would be able to identify it. But will it be the case that he will be identifying or she will be identifying with a good accuracy as it was, identifying with these two only? What I mean is, if I just show two types of pictures again and again, then the probability is if you show a different kind of picture which is having dog or cat only, like it is 90% of the chances that kid will be able to identify. But what about this case? If I say that I have shown, dog, cat, lion, horse, duck, these, and then I'm showing, repetitively these, and then I just, find a new picture of, let's say, lion or a duck or a horse, will your kid be able to identify, or your, younger sibling be able to identify with 90% of accuracy? The answer is no, because in that case there will be confusion in mind. Okay, because now the data type has been increased which a kid has to identify. Data type, I mean, over here is the type of pictures I'm talking about. Is it a dog or a cat or a lion or a horse or a duck? Okay, so in that case the complexity will increase for learning. I hope the idea is clear. So similarly, in case of machine learning algorithms, when we feed data to the machine learning algorithms to learn from, when we feed data within machine learning algorithms to learn from, then there are cases that we may feel that okay, our algorithm, machine learning algorithm, has learned because it is giving me good accuracy. Like over here, when it could see only, few pictures or few data points only, but when I, feed him different type of data points and then, make him learn, then maybe he won't be able to, perform with the same kind of accuracy. So there is a kind of trade-off you'll find over here, that okay, we are judging the learning ability, but how does it actually perform? Can I simply say the pictures I have shown him, or, her, the kid I'm talking about, that he has learned everything properly? Will he be able to identify, or will she be able to identify new type of pictures with the same animals? You won't be able to, tell this accurately, because the complexity when you're showing different type of animal increases in that case. So maybe it will decrease. Okay, there is a good chance, provided your kid a good learner, then only he'll be having a good accuracy. I hope the idea is clear over here. So the thing is, when your data size increases, then the problem is, my model will be able to learn or not, or how will it be performing? And can I always say that the data I have already shown to my machine learning algorithm, how is it performing on that? No, that wouldn't be a good judging point or judging criteria, because it has already seen these kind of things. I would like to show him different kind of data then, because in real world what happens is, for machine learning algorithms, you'll be getting more and more data, and then you'll be predicting so many things out there. But will your data be constant always? The answer is no, because it is increasing. So in that case, you want to perform well on the unseen data as well, which it hasn't seen earlier. And this concept is called generalizability. Generalizability. What's that? Let me just tell you that what you have learned from the data, you are able to generalize that. Okay, that in that case, if this is the kind of data, this must be a kind of prediction. If this is the data point, then this kind of prediction must be there. You are able to generalize with. So this is the generalizability problem, which most of the algorithms, we judge on the basis of generalizability, that how is the generalizability of this algorithm. Okay, it depends on the type of data as well we are having. Okay, that kind of distribution our data follow. Okay, I hope the point is clear. The ability to, to generalize over unseen data is called generalizability of our machine learning algorithms. And how do we do that? So as I mentioned, if I keep on showing only one type of data which it has learned from, and I'm showing that repetitively, will I be able to say that, okay, now my learning algorithm can, predict for every kind of data? The answer is no. The answer is no. Okay. So we have to judge it better, that how does it perform. I should have some, partition of my data points, okay, that okay, I will be showing these kind of pictures, okay, and then we'll check on some other set of pictures. If I show the same pictures again and again, the probability is the kid will also be able to identify that, okay, this is duck, this is cat, this is lion. I hope the example is clear over here. Okay. So the point becomes cross validation. As its name suggests, you want to cross validate. You want to cross validate that, okay, whether my algorithm or machine learning algorithm, or simply my kid or my younger sibling, is able to identify when I show him similar type of pictures but not exactly same. Similar type of pictures but not exactly same. Will he or she be able to perform? Will my machine learning algorithm be able to perform? Because many times what can happen is he has learned too much seeing the same picture again and again. Okay, so for the same kind of picture he is able to identify 100% accuracy, but when a different picture comes, then okay, like typeface may not be able to identify what exactly is that. So over here we have this kind of technique which is called cross validation to check for the performance, that how will it perform on some similar, basically from similar domain, some different data. Okay, the similar kind of data we are having but not exactly same. Okay, to identify that we have cross validation technique. So now we will talk about it in detail. I hope the idea is clear. The example with the kid, and one more example if I would like to give, even if there is no kid, I'm talking about some, let's suppose 10-year kid, 10-year child, even for him learning something like Hanuman Chalisa in first time may be difficult. Hanuman Chalisa I'm talking about, there are so many lines within it. Okay, and for many like Sanskrit may be difficult, so learning that may be difficult. But if you repeat the same kind of data, if you feed same kind of data again and again, then maybe your child would be able to, or your sibling would be able to learn that easily. Okay, so this is the kind of scenario which happens in machine learning as well, that either you show only small amount of data, then your machine learning algorithm will give good result for only that type of data. But if you present some new data, it will be not performing well. And similarly, if you provide some complex data, but provided you have trained it so many times over the same kind of data, let's suppose there are thousand millions of data points. If you have trained a machine learning algorithm, for many of iterations, that means you are just showing that data again and again. So what will happen, if he will be able to, or machine learning algorithm will be able to learn from that. But whatever the new data, then again there will be something which we have to discuss about. Okay, that will it be able to perform on some new kind of data or not? Will it be able to generalize? Okay, what is the generalizability of this kind of machine learning algorithm? So that is the key point over here. Okay, so let's talk about why do we need cross validation. So basic need I have given you basically. Okay, we want to cross validate that how does my machine learning algorithm will be performing, okay, when I present some kind of different data. So cannot be the case that whatever data I'm having, I will simply train on that completely and then ask, okay, tell me now. And from, by picking up one data point from the same data, that, okay, what should be the prediction for that data point? It has seen this data point, it will be telling exactly. But what about some different kind of data? Because machine learning algorithm is learning something, so we should be able to identify, okay, can it perform on some unseen data or not, something like that. So cross validation helps in assessment of the models. Okay, that how does my model perform? Basically, what is the learning capacity of my machine learning algorithm? Has it learned something good or not? Or is it or was it something it has just mugged up everything kind of stuff? Okay. Second point is utilizing data efficiently. So you have abundance of data. If you have abundance of data, would you be using complete data for trading? No, the answer is no. You will be keeping some data aside just to check on that, and just rest of the data you'll be using for the trading. so that okay, it learns from this and then can tell okay that what whether this kind of data on this kind of data it will be able to perform or not. So just to give you a simple example, let's suppose you had, you know, 3 dog pictures, 5 cat pictures, 2 lion pictures, and something like this. Let's suppose 6 duck pictures. Then what you are doing is you are taking 2 dog, maybe 3 cat, 1 lion, 4 duck pictures, 4 duck pictures to show to a kid. Okay, to show a kid, and then that kid is learning. Okay, that okay, this is a dog, this is a cat, this is a lion, this is a duck, and then you are showing rest of the pictures. Okay, he has not seen that those pictures earlier, but it belongs to the same kind of, you know, same type of category. Basically the distribution, if I talk in some technical terms, distribution means it is following same kind of domain which we had already, basically dog, cat, lion, and duck. Okay, so will the kid be able to identify? That is something like this. So we divide our data into some parts so that we can check, one part we use for training, other part we use for testing, that whether my model has learned it properly or not. Now hyperparameter tuning, this is the important concept. So let me just give you a brief example for this, that what exactly is hyperparameter tuning. Okay, so most of the time, just for an example, I'll give you just one simple example over here. Okay, so for an example, you would like to predict, okay, predict the house prices, okay, and there are, let's suppose, 2 3 parameters associated with it. X1, sorry, not, let me write it as feature, yeah, feature 1, feature 2, feature 3, and feature 4. Okay, something like this I'm having. Okay, so with respect to this, you'll be learning to predict the prices of houses, and there are these kind of 4 features you are having, which, you know, you are using to predict the prices. Okay, now the thing is, what should be the kind of a relation with respect to the output you must be having. For an example, let's suppose y is the house prices you are predicting, and you want to say the value of f1, times some parameter a, plus f2 times some parameter b, plus f3 times some parameter c, plus f4 times some parameter d. So let's suppose this is a kind of equation you want to use to predict. So that's, yes, this can be done. And what our machine learning algorithm will learn, that what must be the weightage of feature 1, what must be the weightage of feature 2, what must be the weightage of feature 3, and what must be the weightage of feature 4 to predict our house prices. And what, how we are, you know, identifying that weightage? With the help of this A, B, C, D. For an example, if I just keep d is equal to 0, then it means for predicting the house prices, I'm not even considering f4. But if I say d is equal to 100, that means my f4 feature matters a lot for predicting the house prices. Are you getting that how my A, B, C, D are, you know, helping out in predicting the prices? So these are just parameters. A, B, C, and D. These are just parameters. Okay, by varying these, I can say the weightage of feature 1, feature 2, feature 3, feature 4, how these are varying. And that's how those are the values which our machine learning algorithms learns. So over here, this is the kind of linear regression example. So when I just, you know, feed my data to linear regression problem or algorithm, it will identify my A, B, C, D values. But just tell me, couldn't it be possible that my equation would have been something like this? Couldn't it have been possible that my equation would have been something like this? And f4, okay, yeah, something like this. Yeah, let's just keep it simple. Yeah, this one. So it would have been possible that my equation would have been like this also. That okay, the power of f1 is a square, which helps in predicting it better. That what exactly are my house prices going to be there? Because see, we are able to identify the weights for each of these by using A, B, C, and D. But what if I say that okay, the values of A, B, C, D I got, but still, my performance is not improving. Maybe something extra I need to do. So in that case, what I'll be doing? I will try, okay, that maybe that f1 itself, its square may be required, or f2's cube is required, or f3's square root is required, or f4 is directly being used. So over here, the thing, the exponent I'm talking about, the exponent of each of the feature I'm talking about, this is not the parameter. This is not the parameter. Parameters are just A, B, C, D, because this is going to be learned by my machine learning algorithm. It will not be learning that it should be square or not, it should be cube or not, it should be square root or not, it should be simple or not. My machine learning algorithm will not be learning that. This is something we have to try. Okay, so just over here, a definition comes of hyperparameter. Parameters are something which our machine learning algorithms learn. What are hyperparameters? Hyperparameters are nothing but these are design parameters which a creator or designer of machine learning algorithm to think about. Okay, that should I take it as square or cube root, something like this. A similar example, you must have heard about k nearest neighbor. Okay, I'm not going to go in the detail. So just take a good example. So you have heard about k nearest neighbor. Now the value of k is a hyperparameter. Okay, once you have chosen, it will try to learn. For an example, let's suppose I wanted to use key nearest neighbor, sorry, something like predicting the labels of some images, and I am using k nearest neighbor for that. So what must be the value of k? I can try my learning my model with the help of some different values of k with respect to k is equal to 3, 10, 15, 20, something like this. So when I just fix one value, then my machine learning algorithm is learning from the data something. But when I have decided that, okay, within this machine learning algorithm, I can change this parameter, I can change this parameter, I can change this parameter, then which I can decide, then that is a hyperparameter. Something which my machine learning algorithm is not learning. Now, to identify what are the better values of hyperparameters, this cross validation comes into the play. So we have gone too much into the detail about hyperparameters for just one topic, that is cross validation. So I hope right now the definition of parameter or the idea of parameter and hyperparameter is clear. Okay, this thing must be clear. Hyperparameter must be clear. The point is parameter are being learned by machine learning algorithm, and hyperparameter are something which are design choice, which once created is not being learned by machine learning algorithm. That is something fixed by us who are designing that, who are just writing that algorithm. Okay, I hope the idea is clear. So just to identify what are the better values of hyperparameters, we again use cross validation, because we will be checking that okay, with this hyperparameter what is the performance I'm getting, with this hyperparameter what is the performance I'm getting, what is the performance with this particular hyperparameter. So whichever gives the best, I will choose that hyperparameter, something like this. Okay, now what about the model selection? If I have multiple models, then I want to find out which is the better model. Okay, so in that case I will just use cross validation. Cross validation is nothing but we are cross validating that okay, whether what is the learning capability, can it generalize or not. So if I have multiple machine learning algorithms, I will identify which one is better, yes or no. Assessing model stability. Okay, just because I have told you that okay, we are going to divide our data into, like as I mentioned, one part we'll be using for training and other part for testing. Okay, so this shows my stability of model, okay, that it is uniform on train and testing if my cross validation results are good. If it is not good, then my model is unstable. Okay, because it may change its behavior if some different type of data comes. Now, handling imbalanced data sets. This is important. Okay, this is important. Imbalanced data set. What is that? Let me just give you an example over here for the imbalanced data set. Okay, so I'll just remove everything over here. I hope you are getting. If you have any doubt with respect to anything I have mentioned, because I'm going too slow to be honest, and there is too much to cover. Okay, we have less number of days and I want to cover a significant portion which is easy for you guys to learn. Okay, so just write in the chat, in the comment, whatever thing you find difficult, whatever problem you face. Okay, so I'll just erase this completely. Now, what is imbalanced data set? So let me just give you an example. So for an example, I was just identifying pictures. So I had, for an example, let's suppose only two category if I talk about the dogs or cat. Okay, and I have images of that. Okay, dogs and cats. So let's suppose I have 50 images or 53 images of cats. So I have significantly, like, nearly equal number of images for both. So there would not be any kind of bias in learning. Bias over here, simply bias I'm talking about, not the actual bias term of machine learning. Okay, that we will be discussing in detail. So there would not be any kind of issue with respect to learning. Okay, because I can see both are nearly equal, both the type of images I'm having. But what if I say there are only 5 images of dogs and nearly, let's suppose, 50 images of cats? Then will my sibling or kid or any machine learning algorithm be able to learn properly? The answer is no, because the dogs pictures are less in numbers and cats pictures are high in numbers. So maybe if if I simply say that, okay, let me just give you another good example for the numbers so that you can get this thing. So let's suppose there are only 5 images of dogs and 95 images of cats, and if the kid or machine learning algorithm for every image says that it's a cat, that for every image it encounters it say it's a cat, so still the machine learning algorithm will be able to get 95% accuracy, because for these 5 also it has said that, okay, it is cat, and for these all also cat. So for whatever is the dominant data type or dominant class, if I just follow that, okay, this is the exact label I'm talking about, this is the category, or this is the animal I'm talking about, then my model or kid will always be, not always, but 95% of the time it will be high, and we can say, oh, it has learned because 95% of the time it is telling me good answer. But is that so? The answer is no, because these were less in numbers. So in that case I cannot justify that, okay, it is performing good. If it would have been nearly same in numbers, then it could be a better criteria to say that, okay, 95% it is giving me good. But in that case, for whatever minor category or class it is having and major class, there will always be some kind of issue over here to tell that, okay, that what is the learning capacity of my algorithm. Because if it just follows, if it just tells that, okay, it belongs to the dominant category or the category which has high number of instances, it would be like majority of the time correct. For an example, just 100 of dogs and let's suppose 10 to the power 6 cats images, what will be happening in that case? Again, maximum times you'll say my machine learning algorithm is correct because it is saying cat always. So that won't be a good judging criteria. So in that case, how can we judge, how we can identify for that case? So in case of imbalanced data set, imbalance means when the categories are imbalanced. For few category or for some category I can have high instances available, but for some I may be having very less, or like in single digit or two digit only, if we are talking about other categories in 3 digit or 4 digit. Okay, I hope the idea is clear. So in that case also my cross validation helps. But how does it help? We have to talk about that. Okay, so I hope the idea is clear that how cross validation can help in identifying what is the learning performance of my algorithm, what is the generalizability of my algorithm. I hope the idea is clear. And the few other things as well, that, okay, I'm judging it. I am using data efficiently, I am able to find, good parameters, good hyperparameters for my algorithm. I am able to choose good model, that which machine learning model is good, whether it is stable or not, how we can perform better on imbalanced data sets. Okay. So these are the types now we will be talking about. Okay. Let's see. So this is very simple. This is the most common one which we just talk about, like simply train and test split. Train and test split. Okay. So what we'll do is simply divide our data set into two parts, and this, this exactly is going to be nearly, this is from 70 to 90% depending upon that. This is a kind of, again, design choice. This is a one of the kind of design choice you can have, or this can also be dependent upon the data points you are having. Basically, how many, what is the size of data you are having. If you are having very large data set, then you can take 90%. But if you have small data set, then you have to choose, 70%, because you want some significant amount of data over which you want to test your algorithm as well. Okay, so 70 to 90% can be something like this. So 70%, if I just pick 70%, so this is 70% of the data, then this is 30% of data. So I'll just split it. And then what I'll do is I will train my model on this particular data. And once it has learned, I will feed this kind of data to identify how does it perform in this. Just for an example, if I say I had cats and dog pictures, okay, and I have divided into two parts, train set and test set. Okay, so within training set, I have feeded all the images, whatever I had of cats and dogs. It has learned something, and then I will test on the rest of the images which were there of cats and dogs. So how does it perform? So this is the kind of hold out cross validation. Hold out, when we are holding this test data set out of our main data set. So this entire data set was the main data set we had. Okay, so this is the normal one. So over here, training takes place only one time, training only once, and testing only once. And this is what happens when we have large amount of data, because if we have, small data set, then we can, change it to a number of ways in which I can identify my model's performance. But if my data set is very large, in that case I'll be using this kind of stuff, where I will be using, I will be training my model once on the training data set, and then testing once on the test data set. I hope the idea is clear. Okay. Okay. So this may not be able to identify. Now, if I talk about the disadvantage, because I'm just splitting it, so there may be a case that, okay, it depends upon type of, data points present over here and present over here. Maybe the distribution may differ a bit. For an example, over here you had some, side views of, more of side views of animal, and over here you may be having, sleeping poses of animal, sleeping cat or sleeping dog. So in that case, my performance may not be good, because within same kind of data also I can have a different type of variation. As I mentioned, that over here my cats and dogs have more of side view images, and over here I may be having more of sleeping images. So in that case, if it has been partitioned like this, then there will be an issue. So I must look for some better idea in which this can also be, some kind of sleeping images can also come over here, this can also over here, so that my model learns sleeping images as well. Okay, I hope the idea is clear. So for a big data set, it performs really well. Computationally, it is good, because we are just training it for once, testing it for once. But it may not be able to perform if within, that data set, some intra yeah intra domain variations are there. Okay, in that case it may suffer a bit. Now this is the most significant one which you heard, k-fold cross validation. What is that? So see over here, what I have done is, I had complete data. This was my complete data. This much was my complete data. Okay. Okay, this much was my complete data. Now what will happen is I wanted to check. So for the similar kind of example, now if I had some side images, let's just some side view images were present over here. Some side view images are present over here, over here, over here. Sleeping images were present, let's suppose, only here. Okay. So I am changing my, this kind of training in a number of ways. So what I'm doing is I'm simply dividing my data set first of all in k folds. So whatever is the value of k, let's suppose again this becomes your design choice for testing. Okay, because what if you fix the value of k, then it is going to be a proper procedure. So let's suppose if k is 5 as mentioned over here, so you will divide your data set into 5 parts. Okay, after dividing it by 5 parts, one by one, each of the partition you'll be using for testing, each of the partition you will use for testing. So maybe for the first, not maybe exactly, so this would be test data set, and then this will become your training data set. In the next time, this will be your test data set, and rest of this and this particular one will become your train data set. So basically now you're changing test data set every time. So in this case, I guess you will be able to understand that, okay, in this case, I will be able to judge the performance of my model better. Okay. Or in this case, I will be able to identify the issues better. I hope the idea is clear, because I'm changing my test data one by one. That, okay, it can be this partition or this partition or this partition. Now, how many times training takes place? How many times training takes place? It is equal to k, whatever number of k cross validation, k fold cross validation you are checking. Okay, because for each training time you'll be having one testing, and the total test data set you are test set you are creating is equal to your k. Okay, because k fold means you have divided into k folds, k partitions. Now every iteration, in each of the iteration, you'll use a separate partition for testing. Okay, I hope the idea is clear. So it is good, it will be able to address the problem of what we had earlier. If we have some intra-domain variation, it will be able to identify, but the problem is computational power. Because you are, see how many iterations you are going on, how many times you are training your model 5 times. So just think about this. If your data set is very large, very large, in that case training your algorithm 5 times will consume a lot more time. Okay, so if you have small to like medium size of data, then it may be fine, but still computationally it will be heavy. I hope the idea is clear. Let's move on to the next one. Leave p out, and also the other example is leave one out. Leave one out. So it is similar to k cross validation only. The point is over here you are talking about leaving p data point, and for LOOCV p is equal to 1. Okay, p data point you are talking about, p partition nahi. It's not about the p partition, p data points. Like in k cross validation, k fold cross validation, k partitions you created. Within each partition you can have a number of data points. Just to okay, let me just go back. Let's suppose if your data number of data points you are having 1000. Okay, and k fold cross validation you want to try. So let's suppose k is equal to something like 20. K is equal to 20. So if you just divide n by k, what do you get? It's 550. So that means within each partition will have how many data points? Each partition will have 50 data points. 50 data points, because you have created 20 partitions, and within each partition you will be having 20 data points. I hope the idea is clear. Simple. Now for this one, if you have let's suppose again n is equal to 1000 data points, and p is just let's suppose 20. Okay, let's say p is 20. So that means within testing you will use only 20 data points. 20 data points altogether you will be using, 20 data points. Okay, and rest of the 980 data points which are left, you will be using them for what? You'll be using them for training. Now the point is, in this leave p out of cross validation, you will keep changing on these 20. For an example, if I say simply that okay, this is kind of, this is the example of leave one out, leave one out, because I'm just, testing on one data point and training for entire data points. For all the rest of the data points, I'm training it and testing on just one data point. And then in the next iteration, I have picked up another data point for my testing. So for training, I'm using rest of the data point. For third iteration, I'm using third data point for my testing. I'm using rest of the data point for my training. I hope the idea is clear. So just to give a better insight with the help of some numerical values, let me just put some values over here. So for an example, if you had p is equal to 20, as I told you, so what you will be getting is, what you'll be doing is, if this was the complete data you are having, so initial 20 data points you will use for testing, and rest of the 980 data points you'll use for training. Okay, now this is iteration 1. In iteration 2, basically the second iteration, the second step of training, or second step of cross validation, what you will do is, within the same entire data set, you will leave one data point and then you'll talk about this thing, next 20 data points, next 20 data points, and use this one and rest of the 979 and this one data point you are left with. So all in all 980. So use these 980 for the training and these 20 for testing. So basically what you are having a kind of window which you keep on sliding. You are having a kind of window which you keep on sliding. I hope the idea is clear. Okay, this is the idea for your leave p out. So within this there can be a type. Okay, one can be sequential, one can be random, one can be sequential and one can be random. So what I have talked about is sequential. Basically you have created a window and then moving it one by one. Okay, so how many times you are going to train this? If you are having any p value, how many times you are going to train it? In that case the value is going to be n minus p. I guess n minus p would be the value or not. So if it is 1, you are going to n minus 1, yeah, n minus p plus 1, n minus p plus 1, yes. Okay, if p value is 1, we know we are going to train for n times, yes, because every time I will be checking for each of the data point. So for each data point to be used as testing, how many total iterations I'm going to have? It is going to be n only if I'm having n data points, because for each iteration I will use one data point as test. Okay, like this, like the example mentioned over here. So total number of iteration I will be having is n minus p plus 1, n minus p plus 1. Okay, the idea must be clear. Okay, if I'm talking about the sequential one, okay, sequential one. If I talk about the random one means I am just picking up any p points from my data sets, In that case, how many iterations will be there? It will be equal to ncp. Out of n, what are the number of ways I can pick p data points? So picking those p data points, it would be giving me the total number of iterations I'll be having. That okay, which p points I'm picking, whether it is this and this. If I talk about p is equal to 3, or it is going to be this or this. Okay, so it completely depends upon which p points I'm picking up out of n. So that will be giving me the total number of iterations, okay, for my cross validation. I hope the idea is clear. So we have discussed about leave p out cross validation, where the special case is p is equal to 1, So now the thing is, if my p equals, sorry, if it is sequential, the number of training, not the training, number of iterations will be simply n minus p plus 1. If it is, if it is random, that you are picking up those p points randomly, then it is going to be ncp. And if you put p is equal to 1 in both, you'll get the same answer. See, if you will just pick this p equals 1, you'll get n, and you know nc1 is also n. I hope the idea is clear. Leave 1 out cross validation and leave p out cross validation. In p, you are just picking p data points as your testing and rest of the points as your training data points. Okay. Now for this kind of, cross validation, this is very good for small data sets. It is very good for small data sets because you cannot divide in that case into, like, there would be a kind of issue you are having if suppose you are having only 100 data points. So in that case, what you'll keep, 70, 80, 90, 10. In that case, this will perform really better, okay, when you have small data set. But computationally it is very expensive, very expensive. If your data size increases, data set size increases, then in that case it will explode in a way that it will take very large amount of time, because you are, separating p data points for the test set. That would be meaning, how many times you are training, you can just have an idea over here. And this is very large, to be honest, okay, because if you just compare, if n is in millions, or millions, yeah, millions is a good idea. Just think about n being in millions, or n being in some thousands also. In that case also, this training will take a lot more time. I hope the idea is clear. Now let's just talk about this thing. Okay, stratified k-fold cross validation. So it is like similar to k-fold cross validation only. K-fold cross validation, similar to that what we have seen. The only thing which changes over here is I'm having an imbalanced data set. Okay, as I mentioned, that over there was this case that, okay, if my data set is imbalanced, then in that case I can have issue when I talked about imbalanced one. That maybe, let's suppose, even for the k-fold, let's suppose that my all the minor class, okay, was present only in this area. Let's suppose I had cats and dogs images, and my dogs images are only present within this area, and for the rest of the part there are only cats images. So in that case, my k-fold would not be, giving me a kind of stable answer, or stable, what should I say, stable result, because over here it will be performing good, not performing good, good. So that won't be a good way of, checking out the performance in case of my imbalanced data set. Or even if there is a, like, even if I spread these into different folds, then also there would be some problem, issue would be there. So how to address that? Then what is the thing is, what we can do is, let's suppose, just for an example, so let's suppose we had around we had n is equal to 1000. That means total 1000 data points we were having, total 1000 data points. And let's suppose that for dogs only, we had only, let's suppose 50 images. We had only 50 images, and rest of the 950 images are for cats. So just, if I just, without even learning, if I say that, okay, this image is cat, this image is cat, this image is cat, then I can get 95% of the accuracy for sure. Okay, but that is not a good way, na? Whether my model have learned or not. So there must be some different criteria for that. So yeah, how will I be doing that? The cross validation right now over here. How will we be doing that? So the thing is, and we'll talk about the good evaluation matrices in the next session. Right now we're just talking about the cross validation, how we can do that. Okay, because cross validation is only talking about what kind of partition we are going to take, what exactly is the evaluation metric I am going to use. That is not being told over here, that I'm using accuracy, precision, recall, which we will discuss further. It is just a way of partitioning the data and then using it for training and testing. Cross validation is about that. Okay, so if I had 50 and this is like 1000, so what is the proportion? What is the proportion? It is just, I guess, 5%. So 5% of dogs are present in the entire data set. Only 5% of dogs are there. 5% of dog images are there. So what I'll do is, let's suppose that I was creating k fold. Let's suppose that I was creating k fold. Now, if I'm creating k fold, then let's suppose that k is equal to, let's suppose, 20. K is equal to 20. That means I am partitioning my data set. I am partitioning my data set into k partitions. So let me just erase it. K partitions I'm going to create. So 20 partitions will be there. So in total, there will be 20 partitions. Okay. Something like this is the first partition, this is the second partition, this is the third partition, and so on till last partition. So this is first, second, third, and this is 20th partition. Now, as we know, there are 20 partitions. So just tell me, within each partition, how many data points will be there? So 1000 by 20 is what? You'll get this 50 data points within each. You'll get 50 data points in each. So 50 data points will be present over here, 50 data points will be present over here, 50 data points will be present, 50, 50, 50, something like this. Okay. Now, within each of these partition, k-fold, within each of these partition, I'll keep 5%. That is the actual proportion of my minor class within the total data set. The actual proportion of my minor class in total data set is 5%. So I'll keep 5% on in each of the partition. I'll keep 5% only in each. So what is the 5% of 50? 5% of 50 is nearly 2.5. So it's like I will be having 2 images of dogs over here, or 3 over here, 2, 3. So it will be like this, because I cannot cut image into half and then keep into both. So either I will use 2 or 3. So 2 images of dogs over here, 3 over here, 2 over here, 3 over here, and something like this. So see over here, within each partition I'm having nearly same over here, nearly same proportion of my minor class as I had in actual data set when it was in totality, all combined. I hope the idea is clear. So this is stratified k-fold cross validation. I'm using the k-fold cross validation only, but what I have done is, within each of those partition, within each of these folds I was talking about, I have kept same number or same proportion, not the number, same proportion of the minor class as I had for my total data set, so that I can get a better idea of my learning algorithm. Because if it will be like 1 image over here or 10 image in something else, so there will be a variation in my results. There will be a huge variation in my results, so that can be an issue in that case. Okay, I hope the idea is clear. So stratified k-fold cross validation helps in identifying in the case of imbalanced data set. And what exactly are the evaluation matrices that I'm using? I'm not talking about this right now. We will talk about that in the next of our session. I hope this is clear. So I hope I'm putting enough of effort and you're liking. If you're getting this, please like it and comment your views, please. Okay, and share it with your friends also. So that was all about the different types of cross validation I can have. So over here, just to end this, what can be the disadvantage of this? So whatever are the disadvantages of k-fold, it is similar to that, because I'm having k-fold cross validation only. But the only point extra over here is it is a bit more complex, because now you are dividing your minor class equally into all the folds. So there is an increase of complexity as well, but it is good for imbalanced data set. The others we have talked about were not good for imbalanced data sets. Okay, I hope the idea is clear. Okay, so yeah, so you have done the cross validation. Now what else? So this is the kind of thing which you can have, which you can determine after cross validation you have done. So validation scores. So you must have evaluated on some, putting some evaluation metric fixed, whether it was accuracy, precision, whatever. So you have got for, for each of the type, whatever you have picked up, you have got some validation score, which gives you an idea that, okay, how my model is performing. And if I talk about the k cross, because over here it can be for k fold or some different type, when we had holdout cross validation as well. But this is when I'm talking about the multiple folds only, when we had holdout, sorry, not holdout, the k fold or stratified or leave p out. So in that case, I can average out to know the performance, overall performance of my training algorithm, of my machine learning algorithm. What about the confidence interval? So with the help of the results I have got after cross validation, I can get an idea that, okay, whether my model will be giving 90% of the time good result, or is it 80% of time. Because maybe, let's suppose if I had k fold cross validation, and let's suppose k is equal to 20, then within that, let's suppose in 15 it performed really good, but in 5 it didn't perform good. But if I say in all the 20 it was nearly same, let's suppose over here in 15 it was like 90%, and over here it was 5, in the 5 cases it was like, let's suppose it was giving me 60% of the accuracy, let's say accuracy if I talk about. But if I say some other case in which for all the 20 cases, my output is varying from 85 to 89, this is the accuracy I'm getting for each of the one. So I'm having a better confidence, okay, that for this kind of, that this model is performing really well, rather than this kind of model which is like failing or not giving me good result for some cases, so that is a confidence I'm getting, that what exactly is the kind of performance change with respect to my model when I'm showing different partition of my data, hyperparameter tuning results. Okay, so it helps me in giving me some better hyperparameters, that which hyperparameters I can choose. And the last point, which I just wanted to write over here, but this is something I would like to discuss later on in maybe the fourth session. The third session would be about evaluation matrices, but in the fourth session I'll be talking about variance and bias in detail. This is something very much important topic in machine learning. So cross validation also helps in determining the variance and bias of my model. Okay, bias is something you can see that, okay, how it is performing during the training. Okay, and variance is something that, okay, how it is performing on some unseen data. Okay, something like this, and something like this, a small, just to give you an idea. We'll discuss about it in detail later. Okay, so I hope the idea is clear, that what exactly was cross validation for and what are the different methods. There is a question being asked also, okay, in the sample paper, you can check out that. Okay, so I hope the idea is clear. What exactly is cross validation, what are the different types, what is the need, why do we do that, what is generalizability, what is parameter, what is hyperparameter. We have discussed all about that. Okay, so if you have liked the session, like it, share it, subscribe the channel, comment down your views. Okay, and in the next session I'll be talking about evaluation matrices. Okay, so see you guys in the next session. If you would like to, like you can join our WhatsApp channel for the updates. You can, join the Telegram group by scanning the particular QR code, and you can also follow us on Instagram by scanning the corresponding QR code for Instagram. Till then, take care. Thank you guys. See you guys in the next session.